Welcome to follow this series of lectures where I will go through the key ideas presented in this book, Back to Reality, a revision of the scientific worldview that came out 2020. The book explores fundamental questions such as what is time, what is space, what is matter, what is life, what is consciousness. These questions at the core of existence imply by their mere presence that our worldview is somehow flawed. Otherwise, we wouldn't even ask, would we? While the scientific worldview, compiled over centuries, is an impressive means to make sense of reality, we should be cautious about our beliefs, since, in the light of history, we see that the rational outlook of reality not only evolves, but at times may even undergo a revolution. For example, the Earth-centered stand held sway for a long time, but eventually had to give way to the sun-centered view. Most people also pictured the world fundamentally as timeless, eternal, and unchanging until Charles Darwin's theory of evolution. So, there is no guarantee that the current comprehension of the world is accurate either. The trouble in revising the worldview is that the accumulation of understanding is predicated on the worldview itself. As Einstein said, it is the theory which decides what we can observe. So what does it take to shift the focus, or even better, to open a view for the whole? At the turn of the millennium, when I was nominated as the professor of biophysics at the University of Helsinki, I began by asking myself, why is it that Charles Darwin's theory of evolution, the basic tenet of biology, has remained a mere narrative? Why is evolutionary theory not formulated as a law of physics? I thought that if evolution were to put in a definite mathematical form of a natural law, it could reveal what natural selection truly is and perhaps also explain the origin of life. What could be a more meaningful goal for a professor of biophysics? The idea that evolution could be written as a natural law may seem far-fetched. However, ever since Galileo, physics has proved to be a successful method for showing that seemingly complex facets of reality confirm the simple laws. After a few years of exploration, I found the evolutionary equation with surprising ease when adopting an old atomistic axiom that everything comprises quanta of light. All of a sudden, a new path opened up to a broader understanding and insight to make sense of all kinds of processes extending way beyond biological evolution. This wide-ranging result is to be expected, for everything changes through time. Logically, all processes contribute to the evolution of the whole universe. Nonetheless, I did not anticipate that this would force me to question some of the most established doctrines as well. When exploring this theory of thermodynamics, I realized that a few notable scientists from the past had already known about it. Although their insights were lost as the scope of this dynamic tenet was narrowed down into mere mathematical models of equilibrium, the original principle explains many recent findings and puzzling observations. This is not too surprising, for thermodynamics is considered a universal theory. Since one's worldview is a crucial part of one's identity, it is common to become emotional and defensive when one's own closely held beliefs are challenged. It is unpleasant to acknowledge that one's convictions are unwarranted or outright discordant. However, in the long run, all realistic views must be welcomed. It is a high time to face it. For all its achievements, the theories of modern physics are excellent mathematical models of static systems, but they do not explain the world in evolution, the process of transformation. In the past, scientific revolutions have been preceded by observations that deviate from the predictions, as well as by disconnected disciplines proposing eerie explanations of incomprehensible coincidences. All these hallmarks of impending change are evident today.
What is the evidence for a grand view?
Let us now embark on the way to a proper vantage point from which many foundational questions can be answered and some exposed to be pointless. Let us look at the data. As startling as it is, data are highly similar regardless of what we look at. The common characteristics, the universal patterns, recurrent themes are evident in immense masses of information called big data. For example, words, war, species, and sales distribute in the same way. There are many short words, whereas only few long ones. There are many small conflicts, whereas world wars are few. Small animals are abundant, whereas big ones are rare. Small businesses copious, whereas big enterprises are few. Cities, citations, flares, and quakes distribute in the same skewed manner. You name it, and the distribution looks the same. The world is not random, but distinctly regular. Could it be consistent with just one single rule, a universal law of nature? Unless headings and units are labeled of different datasets, we're unable to say, when just looking at the data, from where the data originates. As an illustration, the length distribution of genes in a genome looks much like the length distribution of words in a book. The length of words vary from language to language, just as those of genes differ between organisms, but the scale-free distributions are skewed alike. The distributions of animal and plant populations in an ecosystem are skewed like those of genes in a genome and words in a book. For instance, there are many small fish and tree saplings, whereas Chinook salmon are as rare as giant redwoods. Distribution of wages and wealth are also skewed. Many are quite poor, very few are super rich. The size distribution of earthquakes looks like that of activated cortical areas in the brain, with a huge quake being as rare as an immense sensation. Conversely, a slight shivering of the ground is as ordinary as a minor stimulation of the senses. Similarities are found everywhere. There are more and more animal and plant species in larger and larger areas. For example, small islets serve as a habitat to a few bird species, whereas larger islands are home to many more species of birds. The number of vocations too increases as the economy develops across time. Technological progress has created digital careers. This universality is self-evident, obvious, trivial, nonetheless amazing, yet overlooked. So we come to ask, what is it that underlies this universality that I keep referring to as the grand regularity? It's evident in our genes and language, and apparent in the food webs of ecosystems and in the structures of human societies. When similarities range from genes to whole ecosystems, and from fine details of matter to the vast voids of the cosmos, could it be that all processes follow one and the same law of nature? Yet another familiar example of the grand regularity is the branching of a nerve cell, which is similar to the branching of a tree. The trunk forks here and there, while the branching quickens and ends in the many leaves at the top. The distribution of branch length from base to ends is skewed in a universal manner. The units and scales vary from system to system, yet regardless of the source and scale, the form is ubiquitous. Natural spirals such as clamshells, the heads of flowers, hurricanes, and galaxies all whirl in a similar manner. The dense center curls tightly, whereas the sparse outskirts whirls widely. In these cases, the skewed distribution of matter is evident at once, directly, without any analysis or theorizing. The similarity of the data across scales and scope is inconceivably broad. You must regard it as incredible unless you see a common cause. Therefore, let us seek the more general explanation, the greater number of different phenomena that share the same shape. Newton was likewise after the same explanation for similar natural phenomena in his rules of scientific reasoning. At first, it may seem all absurd to compare arbitrary data with no common unit of measure. Nonetheless, this is how we break free from the barriers of fragmented understanding to awareness that the world is everywhere mind-blowingly similar. Contrariwise, our view of reality would be incoherent if we were to describe some particular phenomena as profoundly different from everything else. Yet, scientists do just that. Physicists seem unable, for instance, to relate dark matter or dark energy to anything that we already know. Biologists tend to ascribe evolution exclusively to the organisms, but still being unable to make an unambiguous distinction between animate and inanimate. Likewise, neuroscientists wonder about the sense of consciousness as they fail to recognize the same characteristics of subjectivity and emergence elsewhere. In contrast to these divided views, the universal patterns, the grand regularity, suggest to us that there is a deep unity among the microscopic and cosmic, living and non-living, conscious and unconscious. Could it be that the grand regularity merges across time because the same universal law of nature governs processes of every kind? Okay, the idea is astounding. Even so, could it be true?
What explains the grand regularity?
Many growth curves follow the form of letter S. They are sigmoidal, as scientists say. For example, the bacteria population grows in this way. The growth spurts of children and young people are also sigmoidal. Chemical reactions and economies progress likewise. The French 19th century sociologist Gabriel Tarde discovered that innovation spread similar to epidemics. Invasive species spread like riots. Also in the 19th century, Belgian mathematician Pierre-François Verhulst found a mathematical function that matches many datasets of growth. Verhulst's logistic curve, however, does not say why growth is sigmoidal. It only follows the data. Moreover, variation of fossil diversity in geological strata shows that speciation bursts as the growth curve shoots up. Subsequently, evolution comes close to stalling for eons. This universal pattern of change where events first soar and eventually almost stop is still without a clear explanation. The sigmoidal course of events accumulates from a skewed distribution where extreme values extend way beyond the arithmetic average. For example, there are only few large islands as there are only few super-rich people. As the English chemist Francis Galton and the Scottish doctor Donald McAllister realized, the long tail of the skewed distribution can be squeezed when plot axes are marked at even intervals with orders of magnitude instead of their numerical values. After this mathematical transformation, known as the logarithm, the distribution looks almost like a normal distribution. In other words, the natural distributions are nearly log-normal, but definitely not normal. The Gaussian curve, already familiar from our school days, is not found in nature, only in books. This normally distributed curve, symmetrical about the arithmetic average, would be abnormal in nature, where the outcomes of natural processes extend way beyond the spread of sheer coincidence. Nevertheless, as Gabriel Lippmann said, everyone believes in the normal law. The experimenters because they imagine that it's a mathematical theorem, and the mathematicians because they think it's an experimental fact. In this way, the Luxembourgian physicist reminded us that repetition makes a thing familiar. Soon the familiar notion is taken as the truth, while it may not be true, merely a convention. No question about it, the world is statistical, but nature's statistics are not the random variation of the normal distribution, but the regularity of the skewed distributions. Regardless of the subject matter, the cumulative curve climbs up in an S shape and therefore follows mostly a mathematical form known as the power law, which is a straight line on a log-log plot. At the beginning of the 20th century, the Italian social scientist Vilfredo Pareto and the American linguist George Kingsley Smith realized that the power law is ubiquitous. The rule of thumb is, for example, that 20% of the customers bring 80% of the income, and 20% of the accidents cause 80% of the injuries. The 80-20 rule, a handy approximation of the sigmoid curve, agrees well with the outcomes of many natural phenomena and human activity. Besides the power law and the logistic curve, there are also other mathematical models of data, yet they too are only models. Instead of merely modeling natural phenomena, we're looking for a universal natural law that explains these ubiquitous patterns. The American astronomer Simon Newcomb noticed in 1881, and the American physicist Frank Bedford again in 1934, that the first or the most significant digit is the number 1 in about 30% of the cases, and the number 9 in less than 5% of the cases. This rule applies to number sequences such as the Fibonacci series and the value of a physical constant such as a Boltzmann's constant. The incidence is not random but tends to follow the power law. Why? That's what we want to find out. Regularity is also reflected in the size, form, anatomy, physiology, and behavior of animals. This pattern was noted among others Galileo Galilei in 1638 and subsequently by scientist Otto Snell in 1892, Darcy Thompson in 1917, and Julian Huxley in 1932. Well, the bones of an elephant are of course much thicker than those of a mouse. But isn't it remarkable that for all mammals, the relationship between body weight and the bone thickness abides by the same mathematical law? This isometric scaling, also known as allometry, results from a chain of events where each stage of development follows from all those previous steps, that is to say, from history. Why are these path-dependent passages, such as proportionate growth, similar across species? That's what we seek to find out. In 1926, the American biophysicist Alfred Lotka noticed that in any given period of time, most scientists publish relatively few papers, while only few publish many, such that the number of scientific publications per author closely follows a power law. Derek John de Solla Price, a British physicist, advocated in 1965 a similar model for the growth of citation networks. Today we know that likes per post and tweets per person distribute in the same skewed manner. The English mathematician, physicist and peace activist Louis Richardson noted in 1948 that the destruction of wars also follows a power law. These data are worth pondering. What are the forces that are pulling us? What are we being attracted to? By the turn of the millennium, the physicist Alberto Laszlo Barabasi and mathematician Stephen Strogatz and the sociologist Duncan Watts had shown that the World Wide Web, cell regulatory networks, and metabolic networks and social networks are also nearly scale-free. In other words, the system looks the same even when we zoom into smaller and smaller details. This independence of scale is in line with the power law, the characteristic of the grand regularity. When the provenance of the data is not indicated and the scale is not specified, the plots of different datasets become interchangeable by stretching or shrinking the axis. Obviously, the way in which the data is shown does not change the data itself. That is to say, nature does not distinguish between the animate and inanimate, the minuscule and the gigantic, the basic and the complicated. Scales and other labels are our inventions and conventions. Since the ground regularity is on display all the time, we take its ubiquity for granted and pay it little or no attention. No wonder that the universality was not fully appreciated until recently, when a wide range of self-organizing, spontaneously assembling, organally evolving systems were studied. For instance, the electrical activity of neurons is synchronized like the pulsing glow of a swarm of fireflies. Small robots flock like the birds and fish. Emperor penguins move about in breeding colonies like particles in fluids. If you ask for the reason behind something so obvious yet overlooked, the question itself may already point to the answer. The query makes you aware of what to look for. In general, science focuses on those unknown phenomena that are thought to be knowable. But the cause of a grand regularity does not seem to be contained within our theories, which suggests we need to think differently. We have now gone through the facts, empirical evidence, the ubiquitous patterns of skewed distributions, sigmoidal curves, spirals, power laws, even chaos accumulate from processes over periods of time. So we need to understand what is time. We need to identify the carrier of the time and to understand the driving force that makes things happen.
How are the laws of nature found?
Despite the overwhelming empirical evidence for the grand regularity, we don't have to agree about its significance, for unanimity is not the goal of science. Truth is, as the philosopher of science Karl Popper pointed out, the growth of knowledge depends entirely upon disagreement. We can debate, for example, how similar the datasets really are, as we tend to think that a law of nature means a cause without alternatives. However, the world does not seem to be deterministic, or for that matter, indeterministic. Random processes lead nowhere and therefore deliver symmetrical distributions, whereas natural processes produce skewed distributions. We also tend to think that small deviations in data are due to random fluctuations or eventually measurement errors. However, the variation is not random, but it has its causes, however small and momentary. Since neither determinism nor indeterminism explains the universality of patterns, we must look for a non-deterministic, unpredictable, yet causal law that accounts for historical contingency. According to such a law, there would be no random deviations from average, so to say, from an ideal course of events, but all courses of events would be relevant because even the slightest consequence has its cause. Admittedly, it may seem strange to you that a law of nature could describe regular yet unique processes. Well, it's difficult for us to doubt the truth of our time, just as it was for the past generations to doubt the truth of their time. We must thus prepare ourselves for an unexpected explanation, for we know from the history of science that the revolutionary perspective have often been diametrically opposed to the prevailing opinion. Ptolemy assumed that the sun revolves around the earth, while Nicholas Copernicus inferred the exact opposite. Aristotle thought that the force maintains motion, whereas Isaac Newton understood that the motion continues in the absence of forces. The English natural philosopher Joseph Priestley assumed that oxygen was air from which an imaginary substance, phlogiston, released in combustion had been removed. The French chemist Antoine Lavoisier realized that there is no phlogiston. Instead, oxygen in the atmosphere reacts in combustion. Revolutionary views have often been more straightforward and more comprehensive than their predecessors. People with broad interest are disposed to be the first to discern similarities, which are then organized into a theory. We should proceed likewise. Many changes in the worldview have begun by noticing a regularity. For example, the German astronomer Johannes Kepler realized that the planetary orbits are proper ellipses. Now we see likewise that the reckoning of patterns are outcomes of all kinds of processes. At one time, John Dalton, an English chemist, physicist, and meteorologist, understood that the atomistic idea underlies the regular weight ratios of chemical compounds. Now we should find likewise the axiom that underlies the grand regularity. A law of nature states a relationship. For example, Newton's law of universal gravitation relates the gravitational force to masses and the distance between them. Now we should seek out likewise the law of nature that relates causes to consequences and gives rise to the grand regularity. A natural law explains a broad spectrum of observations. For example, the Scottish scientist James Clerk Maxwell's theory applies from X-rays to radio waves. Now we should find likewise a universal law of nature that explains the grand regularity way beyond our own experiences. The English philosopher Francis Bacon introduced a scientific method to distill a common rule from systematic observations. Natural laws have been found in other ways too. Newton used Galileo's approach, in which one's own experience is mathematized into a general law. According to myth, Newton saw an apple fall from a tree and generalized from the falling apple to the universal law of gravitation. Einstein, on the other hand, mathematized an idea of gravitation and uniform acceleration being indistinguishable rather than his experience into general relativity. Maxwell in turn constructed the theory of electromagnetism by insisting on consistency among the equations that had already been found. In the same manner, the German physicist Max Planck discovered the law of radiation. When equations are derived from equations without a connection to the underlying experience, it is not apparent what the theory means, and the mathematical becomes mystical. Equations are then interpreted as reality instead of reality being structured in equations. For instance, the mathematics of quantum mechanics has been taken to connote that there are universes parallel to our own. Galileo's method seems to yield a theory of physics that is firmly related to reality. So, let us use it to find the explanation of the grand regularity, the universal law of causality, and its axiomatic basis by structuring our experience of time into a mathematical form. Let us look for meaningful explanations rather than intellectual challenges. Let us rely on common sense rather than established theories when interpreting data. Honesty suffices. Let us not embrace an explanation unless we understand it, however celebrated it might be. For an explanation to qualify as such, it must tell us what the thing is, what it does, what its structure is, and what follows from it. Naturally, we hesitate to begin the undertaking. Why should we figure out the relationship between a cause and effect? Are such grand missions not rather the domain of leading scientific teams? Paradoxically, the big questions at the heart of reality are open for anyone to explore. Otherwise, they would not be big. Often, the very thing that is directly under our own eyes is the most difficult to perceive. The foundational questions have, in the past, pointed to the essential truths. They might do it again. So, let us ask them anew. Well, that's all for this time. In summary, my main point was that it's not some minor details that the contemporary science fails to put its finger on, but major issues, existential questions whose revelation requires a new perspective, a paradigm shift. My next lecture will address one of these profound questions, the question, what is time?